Thanks everyone for for voting me in on this program, which apparently was very competitive, as we saw. I feel very much overrepresented by the amount of time that I take in the program, and somewhat embarrassed. But I'll try to sort of make my way through it. This talk, I abbreviated the title because this nice slide theme doesn't work well with long titles. It just looks awful. So you need to have a title that is kind of 30 characters, or it doesn't work. This talk is kind of a reworked version of a talk that I gave earlier this year on an invitation from RStudio Conf. So also thanks for them for sponsoring, because that was sort of a large audience. There were 1,200 people and 600 in a room or so, and I made a much larger effort for my presentation there than I usually do. That is very embarrassing, but so this is. But anyway, there's a couple of nice things in it. So I will say something about new art, spatial packages, and now and then jump out and do other things to make it more chaotic and to try to keep you awake, which is not the easiest thing. So spatial data are essentially everywhere, as we know, and there's all kind of stuff that goes on where you see maps. And the thing is that everyone is now these days is now making maps of all kind of things, and that is kind of challenging, right? There was like 2 days ago there was this tweet from Julia Silch, me making maps but not really knowing anything about maps projections, right? So this is what I feel like every data scientist is nowadays kind of running into. I have spatial data. Well, let's make a map. I have no clue what's going on. Let's see how this works, and whatever goes somewhere, worst case to Twitter. And now Julia Silch is a pretty well-known person in our community and the data scientist. I think she's associated with Stack Overflow. I'm not entirely sure, but this sort of got a lot of responses from people actually giving advice. He had some initial ideas, and so a lot of response came out of this. So for her, this helped, and this, of course, wouldn't help for everyone. So I wouldn't sort of say that this is the way to get your help, but sometimes it is funny and it's useful. So I will say something a little bit about spatial data in R, about simple features, the SFR package that I've been working on most of my time last few years, say something about geometrical operations. There's a lot more going on about simple features tomorrow morning, more in a tutorial style. Say something about sort of the tidyverse, how things interact. There is also a lot more on that in Robin's talk, I think on Wednesday or on Thursday. But this is kind of give you an overview. So the original title was kind of tidy spatial data analysis, kind of sort of going towards the tidyverse, the RStudio community. And I will say something about rasters, arrays, spatial data cubes, and the stars project. So I will say actually very little about other people's packages, right? Because there's a lot of people here talking about their packages that will get their time, and there's other things like packages, new packages like TMap or the Google Waze package from Daniel Cooley, I believe. They are very exciting, but I know extremely little about them, so it's not my sort of, I cannot say much about it. So some personal context: I studied physical geography. I'm a geographer. I did a PhD essentially in spatial statistics and geostatistics. I now teach geoinformatics in Münster in Germany, where I'm associated with the Institute for Geoinformatics. And I did a lot of programming. So originally everything was in C. This was in the 90s, and later on S+, and so on, things that Roger mentioned, and wrote or contributed quite a bit to several R packages in the early 2000s, notably GStat-SP, spacetime trajectories, and a couple more. And recently, so I'm one of the authors of the Applied Spatial Data Analysis with R book that got 2 editions that we essentially wrote after finishing the SP package and a couple of packages that could use these classes. So we had let's say, a coherent framework and could publish that in 2008, and this got a 2nd edition in 2013 because a lot had changed, and we are now essentially sort of again in this phase of finishing up work and might sort of start to publish a book on that later on. Recently, I developed an interest in working with measurement units, and that I came into basically by partly because I inherited a course on spatial reference systems, which I enjoy teaching, but I had to learn a lot about sort of reference systems and where they come from, and their measurement units play a role. This is sort of connected to what Roger mentions. This is this network analysis on packages. On Cron, this is already a couple of years ago, was tweeted by Colin Gillespie, who co-authored the book together with Robin, right, on efficient R programming. And that shows sort of a couple of clusters in the R package network, and you see sort of things, web services, visualization, interfaces to C++, MAS, which is kind of a lot of sort of a mix of applied statistics routines that came with the book from Venables and Ripley. And there's the little SP cluster kind of that is also not very large but very visible. And interestingly, the SP sort of all the spatial packages that sort of have been built around that are the only ones that at least have some domain. Of course, the domain of spatial has, is again all kind of domains like epidemiology and ecology and biodiversity and soil and so on, hydrology. So there's all kind of domains, but they're kind of under a common umbrella of spatial stuff. And it turned out that works quite well. Kind of you could call it the GIS umbrella. I don't use the word GIS a lot, but maybe it works. Or geocomputation, which I also don't use a lot, but it's also appropriate. What makes spatial data challenging? So I don't have a clock right here, so I need to now and then see where we are in terms of time. So the challenges in spatial data is that the Earth isn't round. That we have sort of an pretty irregularly shaped planet in which we live, and it's kind of from a distance it looks like a sphere, and then we start modeling it. We say it's a flattened sphere, but in the end it's not, and so it's not sort of trivial to measure this thing. Yeah, so we use a lot of latitude, longitude, but it's difficult to relate often one to another. So coordinates always consist of 2 or 3 numbers, yeah, and these coordinates really lose their meaning when considered individually. So if we have like a location of, say, this is the location, latitude, longitude, it's really a couple of values that sort of denote that location. We could say, okay, we put it in 2 columns, one we call latitude, the other we call longitude. When we have points, that's easy, we have them there, but the longitude values sort of are useless without the latitude values. Yeah, so it's not like the typical other variables like whatever time of observation or something like that, or ID or last name or so. These things work sort of individually, but longitude and latitude do not work. So they really belong together. That is one. And then the second problem is that the most common form is longitude and latitude, and they are funny. They are really sort of spherical coordinates, and there's a lot of things you cannot do with them. For instance, if you compute distances, and that's what a lot of people do whatever cluster analysis or something like that, or they just say, oh well, we do machine learning. We put, machine learners just need features. We throw in latitude, longitude, and we'll be fine, right? And my feeling is always that we're not entirely fine, right? Because they are slightly different from other features in the sense that they have this property that numbers belong together. They're just not sort of single features, but people do it. And well, if you're successful, of course, you could argue what beats it, right? Why wouldn't you do it? But in any case, the thing is that if you would look at distances between points and use the standard Euclidean distance routine stats.dist, then you don't get distances, unless you're close to the equator, where it kind of is sort of linear related to distances, but otherwise it's not. And you can then of course scale and do stuff, but then you're already sort of working with projected data. The other challenge is that, as I said, the Earth is like sphere-like, and maps and screens are flat, so anything we see is essentially 2D, right? Our retina is 2D, so sometimes we get an impression, right? On the first screen I had is moving, this moving globe thing, so which gives an impression of something 3D, but anything we see constantly is 2D, so anything we see is what we call projected data, yeah? And there's all kind of projections you can take, and they have properties, and they have advantages, disadvantages, and choices. Projected distances are always distorted, yeah? So there's no way of projecting and retaining distances. It just that's not possible. It's like, you know, making an orange peel flat. You have to sort of break it up and so on. This doesn't work. So you have to choose things like preserve shapes, preserve directions, preserve areas, and so on. Then you can do stuff, but one goes at the cost of the other, essentially. So. And then there's a sort of a very nice last thing, that even if you have longitude, latitude values, coordinates, longitude, latitudes, then it's not even unambiguous what they actually mean, because they're related to a datum, they're related to a model of the Earth, and they're different models of the Earth, right? And that sort of matters not always a whole lot, right? As I said here, a datum is unlikely important when you map continents, yeah, but it is when you try to deliver a pizza with a drone or something like that. So if you're sort of doing things where distance of tens or 100 meters or something like that matter, then datums become important. So you need to keep track of datums. Yeah? So if you have longitudes and latitudes, it's not like you're there, you know, as if you know enough or something like that. There's this tendency that these days that everything should be WGS 84, which is the sort of a global datum, but it's not, you know, it's only a partial solution, and it's not likely a problem that's going to go away. Yes, there is things like continental drift and so on. So you know, the Earth is not like a static thing, and so it's doable, but it's work. Yeah, so you need to put effort in that. Now there's this thing called simple features. So the little history is we came up with the SP package like 10 or 15 years ago. Yeah, so the idea came up 15 years ago, and first version 13 years ago, with just points, lines, polygons, and some effort to do grids or rasters, and sort of during that same time there was this let's say this standard in the whatever the standardization world sort of coming up that talked about simple features, that said, well, we can represent things slightly differently and maybe more consistently by calling them simple features, and that comes from the word the word feature. The feature means that it's a thing, it's an abstraction of a real world phenomena. So it can be a type or an instance, but won't talk about that. But it's, in any case, it's a thing that has a geometry. Yeah, so like this table, you know, has a geometry. It means that it is somewhere, it has location, but it also has like a shape, and so we could describe that shape. Yeah, so, and then another thing is that it has kind of properties, like, you know, it's made of wood and so on. It has steel feet and so. So we could describe that, yeah. So part of it is the geometry, and part of it is its other properties. It has a weight and these kind of things. Now, how are we going to describe that? And then we come to simple features, and we say, okay, we're going to sort of describe geometries by sequences of points that we connect through straight lines. Yeah, that makes the thing simple, essentially. Yeah. So no curves. Yeah, that's it. And then we can do with that. We can do points. We can do lines. Sets of lines, we can do polygons with holes and these kind of things. And that's a sort of a way to represent these things. So we represent geometries and simple features by points, lines, or polygons, or by collections of them. Yeah, so you could have like a geometry collection that consists of a line and a polygon. Why that is, we get to that later. So this has been described in documents that you can find online that are for standard documents actually reasonably readable. I would not sort of disrecommend anyone to read these standard documents. They're kind of insightful and relatively well written. So ISO is an organization where these documents end and where you have to buy them for like 150 Swiss franc or something like that. But OGC, OpenGeoSpatial Consortium, is the place where you can find the documents really online in essentially their identical form, just not with the ISO label on them. So this is relatively friendly. The main thing is not that it's sort of written down in standards document, but there is a lot of software that adopts these standards. And software in particular, libraries that have been developed in let's say, that are now under the umbrella of the OSGeo, the open source geospatial community, GEOS and GEDA library, notably, and a couple of other ones. It's adopted by GeoJSON, which is a standard for map information on the web. So it does simple features, but then even much more, a little bit more constrained to also saying that the coordinates should always be longitude, latitude, and should always be WGS84, so the GeoJSON even sort of much more constrains things. GeoSparkle is a sort of a dialect that uses Sparkle, sort of a linked data dialect that uses simple features to describe geometries. It has a couple of encodings, well-known text and well-known binary, and that means encodings really means there are, let's say, standardized ways of expressing how, for instance, a point or a line string is written down that is sort of system independent. Yeah? So if you have different systems, if I'm in R and I'm going to communicate with GDAL or with GEOS or with a PostGIS database, I can use that form of encoding my data to read and write. So it's a communication layer, really. It's an encoding, yeah? And that makes the thing very flexible and powerful. WKB is a well-known binary. Is really the form used by pretty much all spatial databases, so PostGIS, MariaDB, which used to be MySQL, I think, SQLite, and all sort of pretty much all the spatial databases put sort of well-known binary blobs in blobs, big, large binary large objects, and it's there, right? So it's just raw binary data that you can read and write when you can read and write these encodings. The standard, the simple feature standard, not only sort of describes how to represent this data, point lines, polygons, in this way, but also it describes a lot of topological metrics, predicates, and operations, right? So, for instance, you want to be able to compute an area of a polygon, you want to be able to compute the length of a line, you want to see if these sort of, points are not completely messy and sort of mixed up, and do checks. So operations, there are, for instance, logical predicates like, is a polygon valid, is a polygon simple, is a polygon empty, quantities that you want to compute like length and area, dimensions that you want to sort of compute from, is it a point or a set of points, then it's zero-dimensional, is it a linear thing, then it's a line string or a multi-line string, or is it a surface like a polygon or a multi-polygon. And you can also derive geometries, so you can do buffers, centroids, and boundaries, convex hulls, simplify things, line merge. So all these operations that we kind of know from GIS, and that whenever you've worked with PostGIS, you've run into them, and then probably GRASS uses the same terminology, hopefully. They're kind of, these words are basically kind of described in the standards, like buffer should do this, buffer should do that, convex hull should do that, simplify should do that. Not really all of them, but kind of this is how it works. There is sort of, these are operational single things. These are operations on pairs, so you can, for pairs of geometries, you can compute, for instance, the distance between 2 points or the distance between 2 polygons. You can do predicates, you can see whether 2 geometries intersect, right? Meaning that a point is in a polygon, or that two polygons overlap or touch each other, and so on. And there's all these kind of constraints that basically build on the D9IM, the dimensionally extended 9 intersection model, which is a powerful model that if you have time, then I'm sort of, I'll talk a little bit more about it tomorrow, probably. So this thing about being simple and so on looks like, it's a bit of a crazy thing, but it is, whenever you can think of things that are not simple, and I defined here a line string. So this is basically, this says I'm loading SF, and then it says I'm linking to a couple of libraries that I need. If I sort of create this line string here, then you see, oops, it's it's there. So it gets printed directly, and the way it's printed is essentially this well-known text form, right? So by printing it this way, I could sort of send that directly to a database. You wouldn't do it, you would use binary, but anyway, that would work out. You could do this to Sparkle or something like that. But then if you look at it, this is 0, 0, 1, 1, 0, 1, 1, 0, so the sequence of 4 points that forming a line string. If I plot that thing like I did here, then and plot sort of the points connected with lines, you see that this is a line string consisting of 4 points of a line that self-intersects. Yeah, so it's not so, and that is a problem because if I want to sort of find out is this thing simple. Then it will say, no, this is not simple. Yeah? So that's a problem, it's not a simple feature. So I can sort of come up with a line string of these 4 points, I can define it, but later on if I'm going to use this line string, you know, in operations, then it's pretty likely that the whole thing will break down somewhere with an error that says, there is some kind of geometry that you're feeding me, which is not simple, I'm not going to do, this is not a simple feature. Yeah? So I can technically constructed upon construction, this check is not carried out and it's not sort of, doesn't break, but it will break later on. And then if it breaks, then you can use this st_simple function to essentially see if this is simple. Yeah, if I would have done it the other way around, sort of go through this way and then, yeah, then it would be true. Yeah, let's plot it. It's the holidays. So this, you know, oh, oops, doesn't. Oh, I should remove the simple. Yeah. So you can see here that this is not really sort of what I had in mind. Yeah, so if I go the other way, sort of 0, 0, 1, 1, and then 0, 1, then this thing is kind of, you know, this is the line string that is simple. It doesn't self-intersect. Yeah, so let's see if that is true. Is simple, then we see that this is simple. Yeah. So this is true. Yeah. So this is a predicate. This is a binary predicate that says yes, this thing is simple. And the same thing is with valid. With valid, it does checks for polygons, and there is a lot of, you know, anyone who has worked with GIS sort of knows that there is a lot of polygon data that are messy, that are, you know, if you would have like a multi-polygon that consists of 2 rings and the 2 rings overlap or something like that, or you have like, if you have a polygon with a hole in it and the whole polygon sort of halfway overlaps with the outer ring, that, you know, these things shouldn't happen. But you can't check that all the time, but there's an is_valid function that does check these kind of things. Yeah. So these are kind of household maintenance things. And then you can sort of compute new geometries by, for instance, by looking at the intersection of 2 things, the difference or the symmetric difference, and the union of things. Yeah. So that gives all logical operations, but they kind of give the resulting geometries. 2 important special cases that the simple features framework has that the SP framework, for instance, does not cope with, and those are the empty geometries and the geometry collection. And here's an example of where they come from. So if on the left-hand side, you see the red and the black polygon, and then trying to compute their intersection, and as you can see, they don't intersect, right? But if I want to compute that intersection, what should come out, right? So the thing that comes out is an empty geometry, and now this happens to be an empty polygon, and so they're typed empty. You have the empty point, and you have the empty line string, and so on. And it's completely, to me, completely unclear why we have typed empty things, but it is extremely useful that there are empty things, that we have basically, you could think of it as the missing geometry, right? The missing value for geometry. And that is different from like having a coordinate with a missing value. You could also think, well, coordinates are numbers. Couldn't they be missing values? It's a completely different thing. Yeah? That is like, oh, I don't know the coordinate. I only know latitude. I don't know longitude. Yeah, this could happen, right? If you only know like how high the sun comes, you know one of these two things. But this is different, right? This is kind of says, okay, I want to do this logical operations on the two things, yeah, and there is no intersection. Yeah, how do I encode it? It's empty. Okay, it's empty. So it's useful. The other thing is when you do something like an intersection, and you get a mixed bag back, right? So these two right-hand side black and red polygon kind of intersect in an area and in a line and in a point, right? So we have a combination of a point, a line string, and a polygon, and that combination is the intersection of these two polygons. Yeah, so it's a mixed bag, and you have to live with it. This is the way it is, right? So it's useful that you can represent it, and typically it's bad news. Oh, I have geometry collections. Yeah, so typically you want one of them. Yeah, you want either the points or the polygons. So you're going to throw away the rest of them. But first of all, is sort of the question: what is the intersection? Well, it's a mixed bag. Yeah, so there's room for this infrastructure that is important to have, and that makes the whole sort of framework very consistent. And you can see that that in the standards document on simple features that there were mathematicians involved, people who understood like set theory and so on. Let's say they said let's try to make a framework that is complete. Yes, and there is only a few glitches, but otherwise it's okay. So package SF simple features does a lot of these things, and it stores simple feature geometries as a list column. And that sort of, to many of you, that will probably sort of sound like complete abracadabra, right? Which is fine. So let's try to see what we can do. If it does that in objects of class SF, that essentially extend data frames, right? And that also might sound very much abracadabra. And so let's see what that means. So let's see what a data frame is, just for 5 minutes, because we have some time. So who of you knows what a data frame is? Good. Can I ask you to explain what a data frame is? Yes, you said I know what a data frame is.
A data frame is like a matrix, like an XY table with database functions, so that you can merge two different data sets, for example, or that you can extend your existing data set with more data.
Yeah. Okay, thanks. So there were a couple of keywords. It's XY, it's matrix-like, and it's table-like, right? So who can explain me what the difference between a data frame and a matrix is? Yeah?
Types. Isn't it like matrices can only have like numerical types, but data frames can have like characters?
Right, so data frame can have different types in what?
Data. So
yeah, but like in different types of rows?
So different columns would have different types.
Columns will have different types, right? So they're like matrices, they're rectangular, they're tables, and columns can have different types. Yeah, that is sort of the real sort of property of data frames. And if you look at them, what they do, it's it's always like where to start, right? So if I create a data frame, let's say of a data set with a variable A that is values 1 to 3, and a variable B that has some kind of character data, you get this data frame, right? And so this is what you see. This is basically the print method for a data frame. So you see a rectangular table, you see the column names, yes, and you see the row names, they are default, and then you see the values of these table things, right? And indeed, so we have columns with different types, and what data frames, what R does basically is that it stores these things in a list. Yeah, so we can ask, is this a list? Yes, so this list is true. So who knows what a list is in R? So who can explain me what a list is? We see much less fingers. Robin. Yes.
A list is a series of objects that can be any type, including other lists.
Right, so it's a series of objects. They are stored in
a list.
In a list, right. Yeah, so it's an object. Yeah, so the general sort of thing we think of these objects as what they are is a vector, right? A list is a special type of vector that can have any types of things in it, right? And so in R, it's useful to understand that vectors are essentially everywhere. So I defined here two vectors here as a range from 1 to 3, and here as a set of 3 strings. So these are all vectors, but they are of a single type, right? They are of character type, or they are of numerical type, and so on. And list is sort of the generic vector that can have anything, that sort of collects anything. So a list is a vector that has some length, and so data frames are lists, right? But data frames are special lists in the sense that we could sort of look into the list by looking at the list extraction operator, sort of, give me element A of this list, yeah, and I get this element A, or you can say, give me element B of this list, and I get this, which is then the character vector turned into a factor. But that's another story. So why I'm telling this, the thing is that data frames are essentially column stores. Yes, column stores is a sort of a database, an ID in databases. So if you are familiar with databases, relational databases typically are record stores, right? So they you say, well, this is how a record looks like. Record has a first name, last name, age, and so income, everything. And then you put a lot of these records in the database. And so it's collections of records. Whereas in R, we work typically with tables in terms of collections of columns. Yeah? And this is sort of what a data frame really is. It's a collection of columns. And the thing is that these columns have to have the same length. If I'm going to try to define a data frame with different length arguments, then it will sort of complain. Yes, this is not going to happen. It says different number of rows. This generates an error. I cannot sort of combine these. I can, of course, combine these into a list, but it's not like this will be very useful for doing analysis or something like that, because we would argue, how does the third record of this list look? If we think of data frames as things that have records, then really we are there, right? So we think of this, yeah, as this of the third record. So rows, we think of records. And columns, we sort of, the list elements A and B, we think of as columns, right? Yeah. So then data frames have a couple of other things. They have so-called attributes, like a lot of sort of, so most R objects are vectors of some kind. Yeah, either they are numerical or character, or they are lists, like generic vectors that have sort of elements in them, and they may have attributes, and attributes are kind of the metadata. We think of them as metadata, and so if they are attributes, and the attributes are names, they're the column names. So data frames will always have named columns. If you don't give it names, it will create names, like here. If I say, well, just create this thing from this, yeah, then it will sort of create default names, which are pretty much terrible. It creates them, tries to create them from the argument, but it's named. Yeah, there will be a name. It has a class. The class is data frame, and it has a row names attribute, which is essentially the row names which are given here by default. I could sort of override that. But there is nothing that sort of withholds you to corrupting these things. For instance, I could now easily say, well, I'm going to change this row names attribute into something that is, doesn't have length 3, but has length 2, right? And then I have like a data frame which has a corrupt row names, because row names is now length 2, where the variables have length 3. Yeah? So let's see what happens. So something is printed, but I get a warning message here. I have a corrupt data frame. So the print method here does a check for me, yeah? But nothing sort of... I'm sorry? Because of this is like... I see, it's sort of, the screen is too large. Okay. Here it was. Can you... Is this like... I'll see if I can make this screen a little bit sort of... This should be better, right? Yeah, good. Yeah, so you can. So it's just an object, right, with a class and with has properties and so on. I can go along and do all the things that we know that shouldn't be data frames and do things with it. But I don't want to do that. But it's interesting that, well, this is basically where S4 came in and said we need to have more formal classes and so on. But it's still interesting that right now, essentially the S3 classes like data frames are still kind of ruling stuff, and all they're fairly unsafe, and it's unclear what a contract with the API really is. It's working, yeah, and everyone uses it. Now we're coming to list columns, yeah. So we have here two simple columns. One is numeric, A, and B is of type factor or character, doesn't really matter. So what if I sort of add to that something that is a list column, and it has a list of length 3, for instance, with some irregular data, yeah? Then I can see, doesn't like that. No, it doesn't like that, but it's really the data frame function that doesn't like that, that says, this is sort of too messy, what you're now providing me, but I can easily add a variable called list column that has this element here to this data frame, and then have this thing, yeah? And what you now have is essentially a data frame with the columns A and B that we already knew, and a third column in it that is not of a simple type, but that is essentially a list that has the right length, but that is kind of a messy type, right? It has differing number of elements, yeah? So they could be like pointers to records to which I have a connection or something, right? You could sort of put a graph, sort of a graph structure in this kind of thing, and that makes it very powerful. That you can sort of, that columns don't just have to be of a simple type, yeah, of numeric, factor, character, time, or something like that. They can be of more complex type, and that is exactly what we do with this list column thing in simple features, and then we sort of put more complicated things into list columns, things like multipoints, like line strings, like polygons, multi-polygons, geometry collections, anything. We just make sure that the list column has the right length, yeah, and that we put it in a data frame. And we can do the same thing with tables, essentially. How does that work? Well, this is what you see. Here you see a printout, basically a table printout of tables. Tables have slightly nicer print abilities than data frames. The RStudio team put a lot of effort in doing this, although some people will not like, these kind of little things that less significant digits get other colors and so. But it's good fun. Here you see that we have a table with 4 regular columns and 1 geometry column with a points. This is the Muse dataset where we see the geometry is essentially put in a list column where you can see that the type is here point and the units are meters. And here we see the North Carolina dataset where we have multi-polygons with degrees as units in sort of a list column in a table. Yeah, data frame does essentially the same thing. So this is like what we call an SF object that knows that it has attributes, but it also has a list column with the geometry, and that the geometry column has a particular name that doesn't have to always be the same thing. So we see the geometry list column essentially as a column in a data frame, and it has a particular class. It's of class SFC. I don't know why, as simple feature geometry collection or sort of set of geometries. They are here, and a single element of that is then again a class thing, which is a feature geometry, which is an object of class SFG, a simple feature geometry. Yeah? So the list column is a collection of these SFT objects, really. And the feature that, as we think of, is then a record in this data frame or in this table, so that has a geometry and it has a set of attributes. But of course, it's not the way it's stored because it's a column store type of thing. Yeah, but we think of records here as features. They have properties, non-geometrical properties and geometrical properties, right? So this is kind of is the framework that SF uses, and that is, so it is really, these objects are really data frames. Even if they're tables, they claim to be data frames. You could argue whether they are, but people say they are, so we'll believe that. Good, so that's an important difference from sort of the whole SP framework, where we had objects that kind of behave like data frames, but that are not data frames. And that turns out to be the critical thing for data to work in the tidyverse, because tidyverse just wants to have data frames to be column stores with equally sized columns, and not sort of objects that pretend they can also behave like a data frame. No, they have to be data frames in that sense. Yeah. So this is really kind of the question, like, where does a data frame start or where does it end, right? What is it, sort of, how is it represented or how does it behave are two different things. You can't mess with this, and this is kind of, this works then in the tidyverse. So how do our individual geometries then stored? Well, this is a slide that I created to sort of point out the 7 simple things we can have. We can have the point. So a point is really sort of stored as a vector. Yeah, so the thing that I showed you here, the ST point. So I'm now going to construct a point, and I need 2 coordinates, like 0, 2, and it's a point with coordinates 0, 2. But I can also have, like, 3 coordinates, and then it says point Z, or I can have even 4 coordinates, and I have a point ZM. So coordinates in the simple feature framework, really sort of most cases you will run into are 2-dimensional, have X and Y, but they can have a third, and the third can either be a Z or can be an M, and they can have 4, and then the third is the Z and the fourth is the M. You can also make a point M, but I need to look up how that works. Dim is XYM, like this. XYM, yeah, and then I have a point M. And now you wonder, like, what the hell is going on here? Well, it is, you know, to some extent convenient to be able to do Z, because geometries are, right, our geometrical world is, we think of it as 3-dimensional, yeah? So it's not such a stupid idea to be able to represent points in space as 3-dimensional coordinates, right? GIS put aside, sort of real world, here physics and so on. Yeah, it's good. So that's the Z. The M is a little bit more difficult story. It's called measure in the standard, and the standard is not very clear about what you should put into it, but it's something else. Yeah, so use the M for something else, and that's a nice invitation to do things. And you could think of properties of coordinates like, what is the measurement error or so, right? If you take a GPS measurement, you get XYZ coordinates, and you get all kind of information about sort of errors in horizontal and vertical. You could try to squeeze that back to a single number and sort of say measurement error. You could also think of putting time in there, right? So it's a number. We can encode time as numbers, then we lose sort of some of the reference, but we can go back. And so Anita Graser, one of the famous QGIS developers, does that currently to represent trajectories and line strings. Yeah, so he has coordinates X, Y, and then puts timestamps into the M, and you get a trajectory. Of course, the challenge there is that if the trajectory self-intersects, which they often do, right? We always run back and forth to the coffee, and so we'll constantly self-intersect with ourselves, with our own coordinates. then the thing is not valid because or is not simple, because simple looks just at x and y and doesn't look at that the third one might be time or so, that is a trajectory. So you can store things like that, but then using using the machinery that you would like to use will be challenging in the next step. So it's not like trivial. So this is what the potential has: x, y, z, and m coordinates. In most of the cases, we look at x and y because we do geographical data. But there's room for that z and m. So a point is just a vector. It's printed here, but it's really sort of it's really sort of, what is this thing? It's just a numerical vector of length 3 with these numbers. Yeah, it's nothing special. Then multipoints or line strings are sets of points, right? Both are sets of points, and they're stored as a matrix where we have the coordinates in rows and variables in the columns. Yeah, so that is the simplest you can get, and then it's a 2-column matrix for x and y, and 3-column for x, y, z, and so on. And then we get other things like multi-line strings, so sets of line strings, and they're basically a set of line strings, so we make a list of line string matrices. Yeah, it's a list of matrices. For polygons, we have a similar thing. Polygons are represented by a ring, an exterior ring with 0 or more holes in them. Yeah, so there might be 0 holes, there might be more. So any sort of ring that follows the first ring is considered as a hole. And that again is a list of matrices, right? And then we have multi-polygons, which is a list of polygons. Yeah, so you get sets of sets of sets of sets of sets. And geometry collections are a list of type geometries. So whenever we have a set, whenever we have a simple set of coordinates, we put them in a matrix, which is the most natural thing for R to do. And if we have sets of those, we put them in a list because they can be of all kinds of sizes, right? The hole is typically smaller than the exterior ring and so on. So whenever there is a set of irregular things, then it becomes a list. Whenever there's a set of points, it's a matrix. Whenever there's a single point, it's a vector. So it's really sort of takes the simplest form that I could think of doing this thing in R. And this is so how things are stored. So you can really, that means that you really can get to the individual coordinates when you have an SF object in R. You just need to accept the logic of nested lists, yeah, because at some stage you just have nested lists. So if I have a single exterior ring and no holes, it's still a list of length 1 with the exterior ring. That is how these things are stored. And then, of course, they are printed in this way, like the way you see well-known text, because you can print them as R objects, but that doesn't really help much. Yeah, so then if we use this package SF, then we get this message: I'm linking to GEOS library of this version, GDAL library of that version, and Proj4 of version of that version, and so on. And this gives a little bit sort of the current dependency tree of things around SF. There are now something like 70 packages, 70 other R packages using SF in one way or the other. And SF uses a couple of other packages. For instance, it can use tidyverse packages to do sort of spatial tidy things that we'll show a few of this in a couple of slides. But it doesn't sort of depend on it hard. That is why this is a dashed line. So you can use SF without sort of tidyverse. Tidyverse is like 80 packages or so it's pretty heavy. So you can use SF without doing this. This is loaded on demand. There is a connector to DBI, so that is a sort of a generic package that sort of has connectors to all kind of relational databases, and that is basically used to read and write to spatial databases directly, which is useful. Another way of doing that is through the GDAL library. You can also read and write to spatial databases through the GDAL library. So GDAL is a library that, or GDAL as Roger calls it, and other people do. It's mostly for I/O, so it reads and writes raster and vector data, does a couple of web service things, connections to databases, And there's a couple of geometrical things, but for that, it really uses the geos library. And there is a sort of a complexity that, I think the complexity is Mac OS X. When you want to compile, things, get things going on cron, and you want to have a binary package distributed on cron that uses external libraries, you need to do a little bit of work, yeah, because cron provides Windows binaries and Mac OS X binaries for you, yeah, but it has to compile them. So on their compile farms, so to speak, all these libraries have to be installed, yeah. Now, GDAL is pretty much probably the most challenging sort of, see somebody nodding back in the back, is definitely the most challenging sort of external dependencies that cron has ever had and still has, because it's a library of libraries, right? It just doesn't do all these things, reading and writing formats by itself, but it uses like an array of like 50 other packages to do stuff, yeah? So for XML, it uses libexpat. For JPEG, it uses OpenGeoHub. For GeoTIFF, it uses libtiff. For an endless list of libraries that GDAL really sort of abstracts on, yeah? But it doesn't work on its own. It really needs all these libraries. Now, if you sort of, if you are lucky and you work on, relatively lucky, you work on Linux and you have all this stuff installed on your computer, you can say, oh, compile this thing, and the whole thing works, and okay, then you're lucky. The thing that what cron does is it says, I'm not going to make binary packages that make any assumptions about your computer. Yes? So if cron would say, okay, I will compile this GDAL or this RGDAL or this SF package for you, but it will only work if you install GDAL, yes, then hell would break loose, because how do you do that? There are 5, 6, 7 different ways of doing that on Windows. There are 15 different ways of doing that on Mac OS X and so on. So what cron says, okay, we're just going to distribute binary packages that are self-contained. The only assumptions that these packages make is that R is on your computer, yes, and that you have a proper operating system, yes, that it runs Windows or Mac OS X in some version. Yeah, so these are the only assumptions. It's not going to make any assumptions. So that means that the whole sort of stuff of all these 50 or 60 or 80 libraries that are needed just to sort of have GDAL working are basically in this package. Yeah? So that is why when you're in Windows or Mac OS X and you want to install SF or RGDAL, that you have a download of like 80 or 100 megabytes or something like that. Right? It's installing all these libraries. You don't see it and you don't notice. That's relatively good, but it's all there and it's happening, and somebody else took care of making this work. Now, why was I making that point? Well, it's a complexity. Yeah, so it's something that we worked out, and we are in regular contact with Uwe and with Simon and so the people who do the Windows and the Mac OS X compile farms, and that needs regular attention and updating and maintenance. And things look easier now. We have WinLib these days, but they're still not trivial. So that was GDAL. GDAL is a complex thing. It's a library of libraries. It's a single interface to, I think on my computer, GDAL has 120 dependencies or so. So you can look at, let's see if we can do that. So the shared library of libgdal has these dependencies. Yes, has 110 other libraries that it links to. So whenever I link to GDAL, it links to these things. So if I look at my SF installation, SF, yeah, and then in the lib directory, we see sf.so, yeah, and we can sort of look at where that links to, and you get the same story. Yeah, so this is dynamic linking. It's linking to 117 library. So that is the GDAL stuff, and that of course is augmented with libr, and so the standard thing that any R package will link to. Yeah, so this is dynamically linked. So it is all sort of loaded the moment I. Yeah, so if I update GDAL, then anything should work again automatically. But when you do binary installs on Windows and Mac OS X, it's a very different story. So there's the geos library that does a geometrical operation. Yeah, I know why I went to this long story. So the thing is that you can also use GDAL for all the geometrical operations, but that needs geos to be linked to it, and that is something that doesn't work for some reason with static linking on Mac OS X. Yeah, that is why we need a different interface to GDAL from the one to geos. Yes, this is basically because the way cron is organized, we cannot distribute packages that use geos through GDAL, although that would be easier from a sort of software engineering perspective, yeah, because then you have a single interface. Now you have kind of two interfaces. Yeah? So geos does all the 2D geometrical operations. Flat Earth, yeah, it does nothing with latitude, longitude. It does everything with sort of Cartesian coordinates. Then there is proj4, and it's a somewhat similar story, but GDAL can statically link to proj4, so we do use in SF actually the GDAL interface to projections. Yeah, so that's why it works slightly different from our GDAL, which does not do that, yes, which directly links to proj4. And that's how it is. And then we have links to liblwgeom, which is sort of a library that comes with PostGIS, was developed in PostGIS, so it has all the things that PostGIS has, but that are not in GDAL. They are in liblwgeom, so some of them are good. For instance, spherical geometry, do distances on latitude, longitude, and these kind of things. And then we link through the units package to the units library, which is also a C library that has a units of measurement database, and that does all the units conversions for you. Yeah? So it knows how to go from meters to US feet. This is something you don't want to program yourself. Somebody else has done that, right? And the thing is that is with all the blue stuff, is essentially these have been done, and this is not an R problem, but this is sort of an OSGeo problem, that all the spatial, all the sort of open source spatial projects, Quantum GIS, PostGIS, in anything that is not Java, so to speak, because Java has this Java hurdle, sort of Java can only speak Java, but anything that does C or C++ uses these libraries. So the left three are spatial, the units is not spatial, but it's kind of meteorology, oceanography, or something like that. The climate, it's the UCAR sort of community that developed the NetCDF, sort of did units, NetCDF community. So these are all libraries that are basically used and maintained by larger communities that know their way with this stuff. Yeah? So this is good because then using the same software, of course, has the risk that you sort of use the same bugs. That is, of course, the disadvantage. It's less rich in terms of an ecosystem, but having to reprogram all this stuff is kind of an absolute sort of most stupid things you could think of doing. Yes. So. Really, what we do is sort of writing interfaces rather than do new stuff. Yeah, but that still is fun. So what are the features here? So now I have to hurry. So we extend data frames or tables with geometry list columns. There is sort of fast C++ to and from R conversion. There is spatial indexes that we use in the geos libraries that are created on the fly. Yes, this is a very cheap solution, but seems to work pretty well. That is something that was not present or relatively underdeveloped in ArcGeos that is now available in SF. So that when you have larger data sets, then spatial indexes are your sort of your only way out of getting things done, really. SF has a relatively small API compared to the functions that are available in SP, ArcGDAL, and ArcGeos. We see that there are much less functions in them. I'm very hard to convince by sort of people suggesting, oh, can't we have this function to do that, and so on. And so I'm very sort of conservative in extending the set of functions or methods available in SF, and it has worked well. I have the experience of doing it the wrong way. So, oh, this is a nice function. Oh, this is a nice function. Yes. And then you end up with a huge collections of things that have terrible names, really. Function starts with st underscore. This is how PostGIS also does it. So if we have like is simple, then you say st underscore, and it is convenient because you can sort of on your R prompt you can say like you can say st underscore tab, and then you get all the st functions and you can see what they do. And if you work with RStudio, it's even much more crazy, all the possibilities you have on the command line, really. But as you see, I'm not. So SF in the tidyverse, a few slides. So we can work with data frames or with tables. You can always like do things. You can just work with geometry list columns, but not with SF object. You can create geometry columns and put them in your own data frames and so on. And then you just use tidyverse and everything should work in principle. There's just that if you create SF objects that are kind of objects that are aware that one of the columns is a geometry list column and is maybe useful for certain things, there are a couple of methods that are sort of dedicated or adopted. Filter, arrange, distinct, group by, ungroup, mutate, and select. They all have sticky geometries, meaning that sort of whatever you put in, the geometry will still be part of the output. And there's an st join that joins tables based on spatial predicates. Yeah, so joining tables, like merging tables, merge in base R, or join left, join right, and so on. And in dplyr, sort of merge records based on attributes, but we can also merge them based on spatial predicates. For instance, two things, overlap or cover or intersect or something like that, right? So you can throw any predicate in that, and stjoin will join you based on that predicate. And then, for instance, summarize unions, also the geometry by the grouping. Yeah, so it doesn't just compute group summaries on attributes, but also by default unions the geometries, like here. So here we see a little sort of printout of something where we do select from tidyverse. So we select only a couple of records or a couple of variables, and we sort of control the number of significant digits of coordinates that are being printed here, these kind of things. Yeah, this is doing, here you see basically we do a transform, so we transform the coordinates to North Carolina state plane with unit US feet, and that is some kind of projection that you see here, and then you see also that there's still multi-polygons, but you also see that the unit is now sort of related, that we understand that these coordinates are now measured in US survey foot, yeah, which is the proj4 way. I think the UD units way of doing that. Here are a couple of things that excited a lot of people. That is the GeomSF, which is now part of the ggplot2 on CRAN, where you can sort of plot spatial data. And the nice thing that you see, well, I can see it, but it was hard to see on the screen, is that sort of the lines, the white lines, the ggplot, are famous for are no longer straight, but they are curved. Yeah, I transformed this again to US survey feet, but we don't see USA survey feet. We see latitude, longitude, and latitude, and we see graticules on the background. So they are no longer sort of straight lines, but they are kind of reference graticules, which nicely works. And it also does automatic things. If you sort of you want to plot something on top of that has a different projection, then it will auto-project that to the projection of the first argument and so on. So it goes, in that sense, it goes much further than what SF does. Yeah, we can also put like, use facet plots. So the facet plots are kind of the composite plots where you have shared axes. Here we have a shared x-axis. And use that for spatial, for collections of spatial maps that have different, relate to different properties. And this relates to two columns, but of course to use this, we have to first do the tidy data thing, which means that instead of having these two columns, the disease cases in 74 and 79, as two columns, we have to stack them, yes? That means that we have a single column that is now the disease cases, and another column that says this is 74, this is 79, and another column that has the geometries twice, yes? Because that is the tidy data paradigm, that everything is in a long table, that we don't have sort of a single variable distributed over several columns. So we have to do that first, and that is done by the tidyr package function gather. Yes, gathers things. That is like what stack does in base R. And then if you gather things, then you can use the facet wrap and say this variable is going to be the facet variable, right? So people who do this daily find this very intuitive. I can just, I just did it this once. But it's cool that this is possible. It's, extremely cool. It's just much cooler because this is map view, right? And there will be a lot of map view, but this is kind of the nice thing is that this is the same, but it's interactive and it has this background, and you can sort of click on elements, and you get sort of the whole set of attributes in this pop-up table. So this is map view, which is a layer on top of the R leaflet package, which is a layer on top of the leaflet JavaScript libraries and so on. So MapView kind of can do these kind of things. You will see much more of that. Quantities, as I said, so we're working a lot with data that have essentially measurement units. So this is a little bit excursion into that. We can do, for instance, this polygon and find out, create this polygon. As you can see, this polygon are 4 points that have, that are in Cartesian coordinates on the line, but there are 4 points that circle around the pole, right? So these are 4 points. It's 3 points, but it's a closed ring that circle the North Pole, and we can sort of find out what the area of this thing is. When we say it's in projection longitude latitude, it's seen as basically a circle around the pole, and we see that the area in it is this amount of square kilometers. If we would say this is the equidistant cylindrical, so essentially Poincaré projection, so latitude, longitude are x and y, and it is flat, then we get an area which is, of course, 0. Yeah, you can see that these points plotted, they are simply there on the line, right? So it doesn't form an area because it includes the poles. So we get, the one thing to note is that we get measurement units. When we compute quantities, we can convert to other measurement units to make things convenient, and also that depending on sort of the way we look at data, we get different outcomes. Yeah, if I set my coordinate reference system to missing, it will also assume it is Cartesian. Yeah, they're XY coordinates in some unknown space, and you also don't get a measurement unit because it doesn't even know what a unit in distance what it means. And we can also do the distance between these between the polygons and these points, and we get a matrix back, which is a units matrix. Distances in units in kilometers. Yeah, so this is for sometimes this is sort of confusing that your numbers are not simply numbers anymore, but in other cases it is sort of pretty helpful that in the sense that whenever you think that your values are in kilometers, but they are in meters, then that might be pretty disastrous. And whenever this information is available, you can essentially work with it. Now, the second thing is that simple features are nice, but they are just do points, lines, and polygons. And so the question is like, where are the raster data? So any story right now about, any book that would be published like these days about spatial data in R would have like 2 stories. Like there is raster package that does raster, and it does it the same way essentially that it did it 10 years ago. And then there will be, features where a lot of people nowadays advise to use simple features for. And they don't sort of talk very well. So this is sort of work in progress to get, to get a raster data framework that kind of works well with simple features. And let's see where that gets. So first of all, raster data don't fit easily in the simple feature framework. You always wonder, like, is a raster pixel, is it a point or is it a polygon? How should I represent that? Or is it some kind of convolution over an area which might be not rectangular because it's, because it is some kind of a sensor or so. We often see raster data come up with continuous phenomena, although you could represent things like land use or soil type or so, but these are also often represented by polygons. But for continuous phenomena, it's more natural to do, like if you have air quality or temperature or elevation, these kind of things. The raster representation is a more natural one because it's continuous, and the idea of a thing is not so clear there, right? So if you have elevation, a thing could be a mountain, but what is, where does the mountain start, where does it end? And this is where sort of geographic information science tends to think about all these kind of problems, which are interesting. But a geomorphometry person would say, well, here's the DEM, done, yeah, story over. We're not going to discuss where the mountain starts or ends. You have the DEM, go ahead and do whatever you want with it. Is a raster a thing? Is a pixel a thing? And so on. You could, or does the raster contain a thing? You think about object delineation and so on. Data cubes is kind of a more a general concept that kind of can include rasters but doesn't have to. So data cubes are essentially kind of arrays, so data that are distributed along dimensions, and raster data have an x and a y dimension. They have basically pixels aligned with x and y, right? But we can also have like multiple layers, like time or spectral bands. This is what raster does in the raster package, does in raster stacks. But then we can also have time and bands, like 4D data. This is what raster does not do. Or we can have 5D data, where we have time sequences of different spectral bands for different sensors, like Sentinel-2A, Sentinel-2B, Landsat-8, and so on. We can also have like time series for points. Yeah, if we have air quality data, hourly data for points, and that also creates a data cube. Yeah, because we have the same kind of time discretization for multiple sensors. Yeah, so that creates some kind of a matrix, which is a special case of a cube. Data cubes are fashionable but not well defined. Watch out for opportunistic definitions. I said there's a lot of politics, people wanting to sort of claim the topic of data cubes. You find sessions about them on conference right now. It's a pretty generic concept. It's not new. It just sort of goes back to the OLAP, online analysis and processing thoughts of data analysis. And other examples are, for instance, health data, where you have the number of healthy and ill persons by region, by year, and by age class. Yeah, so region is a sequence. Year is a sequence, age class is a sequence. So we have like a three-dimensional cube, a three-dimensional array, and then you have two numbers, yeah, the ill and the healthy person, so it's a 4D array, these kind of things. How will this work in R? Well, we have the raster packages, which is extremely powerful. It works with pipes, what tidy people like, and so on. Simple features don't scale very well for raster imagery data, although I had a recent sort of meeting with Mike Summer, as you can see here. This is Mike Summer. Was not mentioned by Roger in his talk, but this is one of the R Spatial person, very active, also very active on Twitter, and so he has sort of his own sort of package verse, sort of GitHub organizations with maybe hundreds of packages, and a lot of these things are very useful and contain an enormous amount of good thoughts. This is and we discussed a little bit about sort of where raster data is or should be going, and actually in this simple feature framework you might want to sort of come up with a class that represents raster data in a relatively simple way. Right now the things that I'm developing are in the STARS package. STARS stands for Space-Time Tidy Arrays, which is also an R consortium funded project, and does raster and vector data cubes, so array data with reference dimensions. So R arrays will not have like information like how does my dimension relate to X or Y coordinates or latitude and longitude or to time and these kind of things. And you basically keep track of those things so you can do more powerful analysis. That deals with 4D plus raster data, but also with, So the challenges that we want to go on with this STARS project is to deal with higher dimensional data, so more than three-dimensional rasters, more than raster stacks, so to speak, and also with data that sort of don't fit on local disks. Yeah, this is another limitation. Raster basically says, well, I don't care about your memory, but I assume that all my data is on the hard drive, which is also a limitation. And if you think nowadays of working with Sentinel-2 data, then that might not be sort of a realistic proposition unless you are very patient with downloading and organizing. Other non-raster data like origin-destination matrices can be represented easily by this. And this is sort of work in progress to be finished hopefully by the end of this year. Here is a little example where a data set that Roger once selected, a Landsat data set, is plotted. So you see slightly different plot methods than the raster package has. So it's a stack of 6 rasters where they have a joint legends, where the legend classes are basically quantiles of the joint set. Here is a Sentinel-5 data set. So this was like July when the first Sentinel-5P data came down. This is one of the Sentinel satellites that measures air quality. And I gave it a go and sort of looked at, and it's raster data. But the thing is, if you look at this raster, so they're sort of, it is like 100 by 100 grid, but it's not like a regular raster, right? It's a curvilinear raster. So this is a satellite sort of taking a funny path of the Earth, and then you get something like this. So this is sort of a no-go when it comes to really reading things in QGIS, so GDAL can read it, but there is no, let's say the spatial referencing is for every pixel you get a latitude and longitude value. So that really sort of leaves you to how to deal with it. I need to talk to the GRASS people how they deal with this, but this is sort of a no-go for raster and for quantum GIS. So you can't say, read this netCDF file. You have to sort of go into this. This is what I did, and this is sort of the terrible code, how it looks like. So I sort of looked at what kind of this netCDF. First of all, the netCDF file has, the file name is like 2-3 lines or so. So I cut out a file name so you could still look at it, and here it falls off the screen. But I'm reading the latitude grid, which is a raster for every pixel, has a latitude value, and then the longitude grid, which has the longitude for every grid cell, and then the nitrogen, NO2, nitrogen dioxide values. That is the thing that I'm measuring, my sensor data. Here you can see sort of the latitude values, and you can see it doesn't have any referencing because this is the referencing. Yeah? These are the latitude coordinates for every individual grid cell. Then I'm setting the NA mask because the nitrogen values didn't do that by themselves. Must be a mistake because netCDF can do that. And then I hacked some conversion to SF function that takes these two matrices and makes that into a points object, really. So I get points with X and Y, latitude, longitude coordinates out of these matrices, and every nitrogen value as the attribute. And this is a points data set that I'm now plotting, yeah, which is okay. Yeah, you wouldn't notice. You can notice from the round corners that these are points, they are round symbols, but I didn't tell anyone. Right? So conclusions is that we have now an SF package already for a while, and it's getting more and more robust. It provides tidy spatial analysis, so mixes nicely with tidyverse stuff for people who enjoy working that way, and works well for vector data. It has 6 package vignettes for further reading. There's work in progress on tidy raster data, space-time array data that happens in the STARS project. A lot of thanks go to our spatial community and to the R consortium for funding the SF and STARS packages. This funding, it's not that it's so much money, but it really sort of makes me commit to stuff. Yeah, so it's really sort of makes me more productive and then not do other things, of course. That is the bad thing. But it's fun to do, actually. For further reading, there is now, since 1 or 2 weeks ago, there is this our journal paper out called Simple Features. So this is now the canonical reference of the simple features for our package. That sort of also summarizes a lot of the stuff that sort of expounds on some of the stuff and sort of summarizes this talk essentially and gives you the references to all further references to all the standard documents and other packages and things and thoughts. How do I get back? Right, and there is the rspatial.org website where there is also blogs on developments on stars and so on are always plotted there, and there is other developments published there. If you have blogs that you would like to have, so rspatial.org gets a lot of traffic. If you have, I'm very much open for guest blogs. If you have stuff that you think fits in there and want to see they're published, then please contact me or ask or send a pull request and so on. That works quite nicely. Contributions are very welcome there. So thanks for your attention. So we have time for 1 or 2 questions. Yes? Oh, hang on.
So how do these SF objects collaborate with the raster objects from the raster package?
Yeah, that's a good question. So I think that it is sort of some things work. I think that there was a raster package update where a couple of the functions now accept SF object as input. It will simply convert it to SP objects the moment it gets them. But raster is a package that has sort of evolved from doing raster analysis into a package doing pretty much everything. So it even dropped raster analysis at some stage from the title. It says spatial modeling. And indeed, it did sort of do all the things that ArcGeos wouldn't do, like combining geometrical operations with attribute things. That's stuff that now, by the way, SF does do. I didn't talk much about it. But at that moment, I don't think that if you feed it with SF objects that it will return you SF objects in the cases where it generates point-line polygon data. So I think it will always like return SP objects. I'm facing the same problem. So say what Roger and I do is sort of first write basic packages and then modify analysis packages. So I'm looking at now at GStat, for instance, how will that work with SF and with stars, and still work with SP things, right? How can it work with data in two different formats? And I did that once because originally it worked with data frames, and then it worked with data frames and with SP objects, but would do either way, right? So you get ugly code, but things that are useful for people who have 10-year-old scripts that you still want to serve. Yeah. So we are facing some choices there. You can look at what our studio does is just change everything completely every couple of years and get everything mad, but then there is a lot of energy and help and so on and compassion. Yeah. So raster is not. It's challenging. It's a massive package, and we met up. We had also during our studio conference, we had a meeting with Etienne Racine and Robert Heijmans to also discuss stars and where the raster is going and so on. And it's not entirely clear. Robert is thinking of doing a new package essentially. And I don't know exactly where that is or where it's going or where that will be. It will be good, of course, but that's all I know. Yeah, good question. Yeah, Robin, hang on. We have try this one. I don't know if it works. No.
Just building on that question, just building on that previous question and being more specific, I remember seeing a message on the rsig geo list from Robert saying, yes, I'm going to continue to maintain raster, but I haven't seen many updates there.
No, but then the question is, what is maintenance?
Yeah, well,
Yeah, this would be new development, really, rather than maintenance. I
yeah,
would
so
say.
that's my question. Do you think that it's most likely that there'll be a replacement package for raster, or it will just disperse into different things in the future?
Yeah, well, that is hard to tell. Yeah, that is so. So as I said, raster is a massive package, right? That tries to do everything, and I would never try to write something like that, because I know how much work it is. Yeah, that is 10 person years or so. So I'm not going to do this, and I don't see anyone else doing that. So Robert may manage, and maybe he doesn't. Yeah, and we now see that a couple of things that a lot of people do, rasterizing polygons, right? So going from polygon to raster, or from raster to polygons. These two things that you can do with raster, but then there are 3 other packages that have, better performance, or that can do this faster, or that better, or that more clear, or something like that. So these are kind of the sort of the low-level stuff that many people do all the time, and where it pays off. Other packages do raster analysis faster because they say, well, my rasters don't have missing values, so then you can do everything twice as fast. Right? This is the same thing with altrep. That can also do things twice as fast when you know that a vector doesn't contain missing values. You can skip the loop, right? It doesn't. And so, yeah, I think we will see some diversification in the next couple of years, and maybe some kind of convergence after that. Let's see.